Hi, everyone. So this is part one of lecture 2 now. Some of you suggested that I should try OneNote, Microsoft OneNote, so I will do that. I'll see if I like it more. Okay, so according to POR, when some physical process is observed or described from two co-moving inertial frames, the law governing that process must take the same form. We have also discussed that a tool for relating two reference frames is Galilean transformation. Thus, at this point in the course, we would conclude that if a law is invariant under Galilean transformation, then it must obey POR. Later, we will see the Galilean transformation is just simply wrong. It's not the right way to relate the two frames. So while POR is still postulated to be true, it will not be synonymous with Galilean transformation. Instead, we will come up with a correct transformation that is synonymous with POR. And we will see that Galilean transformation is an approximation to the correct transformation, Lorentz transformation. It will be an approximation to that correct transformation at speeds which are much less than the speed of light. So everyday speeds are much, much less than speed of light. Anyway, I'm again slightly jumping ahead. So let's see how this works for one of the fundamental laws of physics, the law of momentum conservation. Okay, so let's say Alice in frame A is observing an air track experiment. Okay, so Alice she's doing an experiment, and she's colliding two objects on air tracks. Okay, and then they recoil at some other velocities. Okay, and so let's say this has V1 initial, and this has V2 initial. And after recoiling, this one will have V1 final, and this will have V2 final. I think they're right. I think OneNote is a little bit better. So Alice is doing this experiment. She doesn't know anything about, so let's say she doesn't know anything about physics, but she knows how to take good data. And she took careful data, and she found that while individual velocities clearly changed, right? V1 initial is not the same as V1 final. It's positive, the other is negative, and velocities could change in some complicated way. So while that change took place, there is an interesting combination that just happens to remain unchanging. So she found that this combo right here, M1 V1 plus M2 V2, stays unchanging with time. Okay. Okay. In particular, okay, it's unchanging at all times, including before and after collision. There's some time before collision, some time after collision. M1 V1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. This is a special case of this. This is called conservation. Again, there are many laws out there. They don't all deal with conservation. This happens to be a law about conservation. And I said laws are relationships, right? So you see this is a relationship between something before and after. So she realized that this combo clearly has a special significance. So she called this quantity MV momentum. Okay, so not only she's a good data taker, she's also a clairvoyant. She can foresee how things are called. Okay, and then in plain English, the statement, this math, the statement is that the total momentum of a system is unchanging before, after, and after collision. Okay, more generally, it stays constant at all times if a system is isolated. So this is her experimental finding, and I'm not deriving this law. This is just an experimental finding that this hypothetical experimentalist, Alice, has been able to make. Okay, so total momentum stays constant in time or conserved. Okay, this idea of some abstract quantity staying constant in time while things that we can see, like velocities, changing, that's actually a hard idea. So when I taught Physics 121 for non-engineering students, they find it really difficult to digest because it's kind of an abstract quantity. What's this quantity? Any case, this is nothing that you don't know. And this is really where the concept of momentum comes from. If this quantity was not concerned, we wouldn't have the word momentum in our vocabulary, at least in physics. I'm not deriving momentum conservation. That's a separate lecture. There's a very interesting story there, but this is a fact. What we want to know now is this. Would the same conclusion be reached in some other reference frame? So let's say there's another reference frame. So this is Alice's frame. So this is frame S with its coordinate. Okay, and let's say there's another reference frame, Bob's reference frame. Okay, so some other reference frame, X prime, Y prime, S prime, and it's moving with some velocity, big V. Okay, relative to Alice. So let's say if Alice is in the lab at Cal Poly, Bob is driving in a car, something like that, and he's observing this whole experiment from his car. Okay, so we want to see whether Bob would also conclude that momentum is conserved. Okay, so that's really the question. Let me go to the next page. Question: would Bob in frame S prime also find a momentum, find momentum conservation? Okay, see if this works. Yeah, this works. So that's the question. And now we use the tool use Galilean transformation to answer that question. Okay, so you see we start with this. We see this conservation. I'm simply going to make the velocity transformation, right? So recall that, so sometimes I use primes for velocities as seen from the primed frame. But right now there's too many subscripts, so I'm going to use still this. Okay, so so how do I relate velocity? I would say v1 initial. That's an Alice. That's according to Alice equals v1 tilde initial plus big V, right? So this is according to Alice, and this is according to Bob. Students are often confused well, they would agree that if V is positive, then this works. But notice V doesn't have to be positive. So if Bob is moving in the other direction, V will just be negative, and this formula still works. Okay? And for example, I can say that V2, say, final equals V2 tilde final plus V, so on. So don't worry about the fact that the final velocity, initial velocity, are not of the same sign, right? So this will take care of this. So for example, it's possible that according to Ellis, V1 initial is like that and V1 final is like that. But if Bob is moving sufficiently fast, according to him, V1 initial is like that and V2 initial is even more like that, okay? You can try and play with it, with numbers, and you will see. This takes care of everything, okay? Okay, so then sub into momentum conservation found by Ellis. So I'm going to call it equation star. Okay, so this thing right here, I'm going to call equation star. Okay, and I'm going to substitute these into equation star. Okay, so what do I get? I get M1 V1 tilde initial plus big V plus M2 V2 tilde initial plus big V. I'm just substituting, just doing algebra. M1 V1 tilde final plus big V plus M2, oops, running out of space, V2 tilde final plus big V. Okay? Not a bad idea for you to pause the video right now and clean this up. It's a good exercise. Okay, so I presume now you've hopefully paused the video and did the algebra. So I'm going to press on. So I can rewrite this. So just clean up. And I will find that it's M1 V1 tilde initial plus M2 V2 tilde initial plus M1 plus M2 big V equals M2 V2 tilde final. Oops, sorry, M2 V1. Just a second. M1, M2. This should be M1. Clean this up. M1 V1 final plus M2 V2 tilde final. So this is initial, this is final. Times M1 plus M2 big V. So what do you notice? What's the magic? That this thing cancels from both sides. And what do I find? I find M1 V1 tilde initial plus M2 V2 tilde initial equals M1 V1 tilde final plus M2 V2 tilde final. Is the momentum conserved according to Bob? Yes. So this is P total initial equals P total final. And by the way, I could call this, I could say that this is P total initial equals P total final. Okay? So Bob says, I found that if I look at this quantity called MV, the grand total sum of all MVs just happens to be unchanging. He would find exactly the same conclusion. Now you see what I mean by form. Okay, so the form of this is the same as the form of this. They have the same form. The difference is that these are untilted and the other ones are tilted. But what does that mean? It means that the numerical values of velocities is different in Alice's and in Bob's frame. Well, we already know that. We've already discussed that the numerical values of velocities, the values of velocities, are different depending on your reference frame. But the form of the relationship between quantities is the same. You just substitute different numbers. Okay, that's what not tilde and tilde really are trying to tell us, or that's what tilde and non-tilde really mean, is that the actual values of numbers could be different, but the form is the same. Or you could just say the form of this, right? So the form of this is the same as the form of this. Or if we include the velocities, if we look under the hood, the form of this is the same as the form of this, okay? And that's what I mean when I say that the form of the law is preserved or invariant. Form of the law, in this case, it deals with conservation. Not all laws deal with conservation. The form of the law is invariant with respect to reference frame change. Or just invariant, because when I say invariant, I mean the same from one reference frame to another. Okay, so the equation looks the same as it was in Alice's frame, except that it has different values for velocity. So for example, V1 initial could be 1 meters per second, and big V could be 3 meters per second. Right, so Bob is zooming that way. Then according to Bob, V1 initial tilde is minus 2 meters per second. The values of quantities are not necessarily the same, but the form of the law stays the same. And physically, it means that if the momentum is seen to be conserved in one frame, then it will be seen to be conserved in another frame. If P total initial equals P total final, then P total initial tilde equals P total final tilde. Okay. The momenta, the sames, are not invariant because velocities are not invariant. But the fact of conservation is invariant. The law is invariant. The relationship between quantities is invariant. And on the homework, first of all, you will have a chance to repeat this argument. Okay, just for your own benefit, of course, you want to do that while closing the notes and closing the book. Try to repeat the argument. If you look at the homework, I walked you through that. And you will see where you get stuck. Maybe you won't. It's fairly straightforward. But you might get stuck. And there is value in trying to figuring out how to get unstuck. That's where the learning takes place. I kind of want you to struggle a little bit. In any case, part one on homework problem number 3 is for you to basically reproduce this argument in order to really understand it. Okay, and you understand when you get stuck. And part 2 is the new stuff. You will see how this works with energy conservation. Again, the same scenario with 2 cards. Hopefully from Phys 1, you remember something about elastic collision versus inelastic. Elastic means kinetic energy is conserved. So let's say if this is an elastic collision, then not only momentum is conserved, but the kinetic energy will also be conserved. So let's say Alice found that, oh, there's another combo. The sum of all 1/2 mv² stays constant. And the question is, will Bob also conclude that. So you repeat the procedure, you change from one frame to another, and you will test for yourself whether energy conservation is invariant. Okay, so that's your homework problem number 3. You can already, get started on that. And on that note, that concludes part 1 of lecture 2.